Damping in an RLC circuit, understanding the Q factor. Introduction. Welcome to this video on damping in an RLC circuit. Today, we'll explore how a simple circuit made of a resistor R, an inductor L, and a capacitor C behaves over time. Specifically, we'll look at how the quality factor, or Q factor, determines whether the circuit is overdamped, critically damped, or underdamped. By the end of this video, you'll understand why the Q factor is so important and how it shapes the behavior of the current in the circuit. Let's dive in. Chapter 1. What is an RLC circuit? An RLC circuit is a fundamental electrical circuit that consists of three components. 1. A resistor R which opposes the flow of current. 2. An inductor L which stores energy in a magnetic field and resists changes in current. 3. A capacitor C which stores energy in an electric field and resists changes in voltage. When these components are connected in series, they create a system that can oscillate, much like a spring mass system in mechanics. The behavior of the circuit depends on the values of R, L, and C, as well as the initial conditions, such as whether the capacitor is initially charged. Chapter 2. The role of the Q factor. The quality factor, or Q factor, is a dimensionless parameter that describes how underdamped, or overdamped, the circuit is. It's defined as the ratio of the energy stored in the circuit to the energy lost per cycle due to resistance. Mathematically, it's given by Q equals 1 over R times the square root of L divided by C. The Q factor determines how quickly the oscillations in the circuit die out. There are three possible behaviors based on the value of Q. 1. Overdamping Q less than 1/2, the circuit doesn't oscillate, the current decays slowly to 0. 2. Critical damping Q equals 1/2, the circuit doesn't oscillate, but the current decays to 0 as quickly as possible. 3. Underdamping Q greater than 1/2, the circuit oscillates, but the oscillations gradually die out over time. Let's explore each of these behaviors in detail. Chapter 3. Overdamping Q less than 1/2. When the Q factor is less than 1/2, the circuit is said to be overdamped. In this case, the resistance in the circuit is relatively high, which means energy is dissipated quickly. Behavior. The current in the circuit decays smoothly to 0 without any oscillations. Why? The high resistance prevents the energy from sloshing back and forth between the inductor and capacitor. Instead, the energy is quickly dissipated as heat in the resistor. Real-world analogy. Imagine pushing a heavy door through thick mud. The door moves slowly and doesn't swing back and forth, it just settles into place. Overdamping is useful in systems where oscillations are undesirable, such as in car suspension systems or electronic filters. Chapter 4. Critical damping Q equals 1/2. When the Q factor is exactly 1/2, the circuit is critically damped. This is a special case where the resistance is just right to prevent oscillations while allowing the current to decay to 0 as quickly as possible. Behavior. The current decays to 0 without oscillating, but it does so faster than in the overdamped case. Why? The resistance is perfectly balanced to dissipate energy without allowing any overshoot or oscillations. Real-world analogy. Think of a car's shock absorber. If it's critically damped, the car settles quickly after hitting a bump without bouncing up and down. Critical damping is often the goal in engineering systems because it provides the fastest response without oscillations. Chapter 5. Underdamping Q greater than 1/2. When the Q factor is greater than 1/2, the circuit is underdamped. In this case, the resistance is relatively low, allowing energy to oscillate between the inductor and capacitor before eventually dissipating. Behavior. The current oscillates back and forth, but the amplitude of the oscillations decreases over time. This is called damped oscillation. Why? The low resistance allows energy to slosh back and forth between the inductor and capacitor, but some energy is still lost as heat in the resistor, causing the oscillations to die out. Real-world analogy. Imagine a pendulum swinging in air. It swings back and forth, but each swing is smaller than the last because of air resistance. Underdamping is common in systems like radio tuners, where oscillations are necessary to pick up specific frequencies. Chapter 6. Visualizing the behavior. Let's visualize the three behaviors using a graph of current versus time. 1. Overdamping. The current curve is smooth and decays slowly to zero. 2. Critical damping. The current curve decays to zero quickly without any oscillations. 3. Underdamping. The current curve oscillates, but the peaks get smaller over time. The Q factor determines which of these curves you'll see. A low Q factor leads to overdamping, a Q factor of 1/2 leads to critical damping, and a high Q factor leads to underdamping. Chapter 7. Applications of RLC circuits. RLC circuits are used in a wide range of applications, and their behavior depends heavily on the Q factor. 1. Radio tuners. Underdamped RLC circuits are used to select specific frequencies in radios and TVs. 2. Filters. Overdamped and critically damped RLC circuits are used in electronic filters to remove unwanted frequencies. 3. Power systems. RLC circuits are used in power systems to stabilize voltage and current. Understanding the Q factor is crucial for designing these systems to behave as intended. Chapter 8. Why does the Q factor matter? The Q factor is a key parameter because it determines how quickly energy is lost in the circuit. A high Q factor means the circuit can store energy for a long time, making it ideal for applications like radio tuners. A low Q factor means energy is lost quickly, which is useful in systems where oscillations need to be suppressed. By adjusting the values of R, L, and C, engineers can control the Q factor and tailor the circuit's behavior to suit specific needs. Conclusion. In summary, the Q factor is a powerful concept that determines whether an RLC circuit is overdamped, critically damped, or underdamped. Each behavior has its own unique characteristics and applications, from preventing oscillations in car suspensions to tuning radios to specific frequencies. Understanding the Q factor not only helps us analyze RLC circuits but also gives us the tools to design systems that behave exactly as we want them to. Thanks for watching, and I hope this video has given you a clear understanding of damping in RLC circuits.